Assalamualaikum warahmatullahi wabarakatuh. In this video presentation, we are going to present about environmental industry. This is my group members. IZZATY MUNIRAH binti Abdul MUNIM, TENGKU FAQIHAH DARWISYAH binti TENGKU Muhammad ANNUAR, JOHARI HAYATI binti JOHARI, TUAN ALYAA SAFIAH binti TUAN ISMAIL, and ISABELLA MAISARAH HANI binti Muhammad SANI. My name is JAWAHIR HAYATI binti JOHARI, and now I will present about environmental industry use fungi, which is bioremediation. Environmental industry is an industry involved in the development of cleaner technologies, waste and wastewater treatment, recycling process, biotechnology process, catalyst membranes, desulfurization plants, and noise reduction. Bioremediation refers to cost-effective and environment-friendly method for converting the toxic and recalcitrant pollutants into environmentally benign products through the action of various biological treatments. Fungi play a major role in bioremediation owing to their robust morphology and diverse metabolic capacity. Next, history of environmental industry using fungi. In 1960s, there are the use of white rot fungi and their enzymes as a biotechnological tool for xenobiotic bioremediation. Basidiomycete is the fungi which used to degrade xenobiotics, which is a foreign substances, in the environment because it is eco-friendly, cost-cheap, and more tolerant to high concentrations of pollutants. Their capabilities to remove xenobiotic substances and produce polymerase products make them a useful tool for bioremediation purposes. The next one was in 1980s. The other white rot fungi, called Phanericate chrysosporium, was proven that it is capable of biodegrading various pollutants. This fungi soon became a model of white rot with the most research. To add more, in 1990s, mycoremediation was introduced with its viable approach for environmental cleanup. Since then, the research in this field has expanded rapidly with a growing number of studies which shows the potential of mycoremediation for a wide range of applications, from soil remediation to wastewater treatment. After that, the use of fungi in removal of E. coli and fecal coliform was first demonstrated in 2005. The mycelium of the fungus was intentionally cultivated to serve as bioreactors for bioremediation of water bodies. The last one was in 2020s, proven that fungi such as Aspergillus niger and Trichoderma herrerianum are effective in bioremediation of heavy metals. It is due to their ability to secrete organic acids that chelate metals and facilitate their removal. Citric acid, which produced by Aspergillus niger, can solubilize metals like cadmium and lead, converting them into less toxic forms that can be immobilized or precipitated out of the environment.
I'm Isabella HANI, and today I will be explaining about my part regarding the importance of fungi species. Fungi species are extremely important in many aspects of life, both in natural ecosystems and humans' activities. So first we will look at the ecological importance. Fungi acts as decomposers. It breaks down dead organic matters in order to recycle nutrients back into the ecosystem. And we have mycorrhizal association. A lot of fungi form symbiotic relationship with plant roots for nutrient and water absorption. And we have lichens. It is important in soil formation and air quality indicator. Next, in medical importance, fungi acts as antibiotics. Species like penicillium produces antibiotics that has been revolutionized as medicine. For example, grisofulvin is an antifungal used to treat dermatophytic infections of the skin and nails. Next, we have echinocandins. Is a newer class of antifungals derived from fungal metabolites that is prescribed to treat invasive fungal infections. And lastly, we have immunosuppressants. The fungi produces cyclosporin, which is essential for organ transplant. So, we're moving on to industrial and food uses. Fungi plays a big role in fermentation. Yeasts like Saccharomyces cerevisiae are used to make bread, beer, and wine. And fungi are also important in food production. Some fungi are directly consumed like mushrooms and truffles, or used in cheese making. For example, Penicillium roqueforti in blue cheese production. And lastly, agricultural importance. Some fungi also contribute in biocontrol agents in order to control plant pathogens naturally by acting as natural pesticides. The fungi species has the ability to kill or inhibit harmful pests, nematodes, or pathogens. For example, Trichoderma species suppress soil-borne plant diseases like root rot and damping off. And we have biofertilizers, fungi are also used as biofertilizers to avoid dependency on chemical fertilizers. For example, arbuscular mycorrhizal fungi (AMF) are commercialized as biofertilizer products.
My name is TENGKU DARWISYAH binti TENGKU ANNUAR. For my part, I will explain the application of fungi in environmental industry. First, mycoremediation. Mycoremediation is a bioremediation that uses fungi to clean up the environment. Is it applied in the environmental industry to first clean up contaminated soil and water, and second break down pollutant into less toxic or non-toxic form. How fungi do it? Fungi release powerful enzymes like ligninolytic, oxidative, and extracellular to degrade pollutant. Most effective in surface or aerobic soil zone where fungi mycelia can grow. Ligninolytic fungi like Polypora sp and Phanerochic chrysosporium can degrade a wide range of toxic compounds. It is cost-effective, eco-friendly, and fits under the category of green technologies or biotechnological solutions in environmental management.
My name is TUAN alias SAFIAH, and now let's explore an innovative and sustainable technology in the environmental industry, which is mycofiltration. Mycofiltration is the process that uses fungal mycelium as a natural filter to remove contaminant from water, soil, or air. It falls under water treatment and pollution control technologies, both of which are essential in today's environmental management. In this method, fungal mycelium is cultivated on substrates such as straw or wood chips, then placed inside sac and submerged in water. This fungal network acts as natural filter, effectively removing pathogen, heavy metal, nitrogen, phosphorus, and a range of industrial pollutants. This method has been proven effective in treating stormwater, drinking water, and industrial effluent. What makes mycofiltration especially valuable is its sustainable and cost effectiveness, making it a practical, eco-friendly solution for modern environmental challenges.
For the last one is biodegradation. Biodegradation is the breakdown of material by living organisms like fungi into simpler non-toxic substance. Fungi from the phyla Ascomycota, Basidiomycota, and Mucoromycota are capable of degrading various common plastics such as LDPE and PET. These fungi secrete enzymes like esterase and urethane hydrolysis that break down long polymer chain. The degradation process occurs naturally without the need of chemical additive or heat treatment. This eco-friendly method offers a sustainable solution for managing plastic waste. It is also support environmental industry goals by reducing long-term waste accumulation, minimizing the environmental impact of synthetic material, and aligning with circular economy principle and green technology initiative.
Mycocycle is a biotech company that uses fungi to treat construction and demolition waste. They use oyster mushroom to turn harmful waste into safe and reusable construction material. The process works in 3 steps. First, the waste is mixed with fungal spore called mycelium. Next, the mixture is placed in a controlled environment for about 4 weeks. During this time, the fungi break down toxic substance and turn the waste into eco-friendly materials. This method shows great result. It reduces harmful chemicals like polycyclic aromatic hydrocarbon (PAH) by 95% and phthalate by 85%. It also creates materials that are fire resistant and water resistant. The cost is low, between $0.07 to $0.17 per kilogram, which is affordable and competitive with traditional waste method. The impact is very positive. It helps reduce landfill waste, support green building, and encourage a circular economy. This method is already being used in the UK and the USA.
My name is IZZATY binti ABDUL, and I'll be presenting about the challenges, the future of fungal technology, and lastly the conclusion. For the challenges, the first one is environmental limitation, which is fungi have optimal pH and temperature ranges, which is they are hardly survive in highly acidic or alkaline environments. They are also have temperature sensitivity, which is affects the fungal growth and metabolic efficiency. These factors can limit where and how fungi can be used for applications like bioremediation or waste degradation. The second one is the safety issues. Fungal spores can pose health risks like allergies, respiratory issues, or infections. The containment and control measures are necessary during the application. Next, for the future of fungal technology, there are 3. The first one is genetically modified fungi, or GMF, where the fungi can be engineered to enhance the ability to break down pollutants or survive in harsh conditions, which is potential for tailored solutions in environmental cleanup. The second one is sustainability, which is the fungi will be low cost and low energy alternative for waste treatment and soil restoration. Last one is space application, where NASA has been exploring the use of fungi in space. As example, how fungi can be used to produce biomaterials and even food in space. Lastly, for the conclusion, to sum up, fungi are an organic and eco-friendly, which makes it a nature-friendly solution to some environmental problems. They have an ability to break down waste, detoxify pollutions, and make the soil richer. Somehow, there are some challenges. As example, they need to grow in the right condition and there are safety concerns. However, the scientists are making these obstacles a thing of the past. With more research and development, fungi will be in a position to help produce a greener and sustainable future.